in any way? I pressed the wrong button. Okay, well, yes, my name is Stuart Clarke. I'm a senior lecturer at the University of Keele in Staffordshire, not very far away from here. And thank you for the invite to talk to you this afternoon. When I was invited, I talked a little bit to Pete about what I might present. And did you want the usual kind of stuff that I present, which is my main sort of research area, which is arid sedimentology out in the Western US? Or do you want something a little bit off the wall that's a bit preliminary, a bit outside my comfort zone perhaps, a bit risky maybe? And Pete was like, oh, go for the off the wall stuff. So we're not going to talk about Utah today. We're going to instead go back to somewhere slightly closer to home and a former life that I had, in fact, and look at some ideas about the sedimentary fill of the North Pennines, and indeed ways in which we might possibly model it, particularly some sort of numerical modeling, which is something that I haven't really played with as a concept since my PhD. Since then, I've been a field geologist, really. So back in the Carboniferous, if you know anything, if you have any experience of the Carboniferous in the UK, you might see the joke in the title, cycling back through an old theme. If you don't worry. I think that will become clear in a second. So, okay, this is, oh, the pointer doesn't work too well. There we go. This is where we are, Britain. Here's the north of England, the North Pennines. The North Pennines is really this upland area here, and the adjoining lowlands to either side. Between Carlisle, Newcastle on the east coast there, Barnard Castle that we all know far too well now, and Penrith down here. So it's this big upland mass. And what I'm going to do now in the next slide is just flip Britain sideways, the reasons that will become clear in a second, just to get your eye in a little bit. So flip it sideways like that, and we're now looking at the UK mainland, or Northern England, more specifically, from out in the Irish Sea. You can see the Solway Firth here, the Scottish border, and the Lake District. Yeah, you just got a feel for that, and that's mainly just to key you into this next diagram, which is one of my favourite diagrams of all time. It's a BGS production, but as you can see, it's got north in a silly direction. So north is pointing this way, and in purple there you can see the coast of Britain. So here's the Solway Firth, here's the Lake District again, coming down to the Southern Lake District there. So you get the idea of how that works, hopefully, because what it shows very neatly is the depth to Carboniferous basement over the north of England. So essentially what we're looking at is the various deeper centres from the north of England where sediments were placed during the Carboniferous period. A series mainly of east-west trending basins, like the Northumberland Trough and Solway Basin through here, Stainmore Trough to the south, separated by some upstanding areas, often referred to as blocks. So the Alston block in particular, which has the little market town of Alston in the middle of it, the Astrig block to the south, arguably the Lake District block as well, but we're not really interested in that. We're interested in this area over here today. And the whole of that area during the Carboniferous was, well, during the early and middle Carboniferous. I think your pointer's died a little bit, which is annoying, but there we are. During the early and lower Carboniferous was mostly at sea level or below sea level, essentially. And into those holes and onto the blocks was deposited a reasonably rhythmic alternations of limestone, siltstone, sandstone, and sometimes coal. And that pattern repeats, roughly speaking, time and time again. And as a result, that pattern got termed a cyclothem, or Yoredale Cyclothem, hence cycling back through an old theme, the title of this. So the cyclothem is defined from the base of one limestone to the base of the next limestone up in the succession, or I should really say the next major limestone up in the succession. And the limestones have names. These are mainly old mining terms, but the British Geological Survey has adopted the same terms to avoid confusion. So the limestones have names, like 4 Fathom limestone down here, Great Limestone, for example. And the cyclothems themselves, the succession of strata that goes limestone, siltstone, sandstone, and sometimes coal, is named after the limestone at its base, a bit like that. So this is the 4-fathom cyclothem, all of this strata in here. That's how it works. Now, the basic, if you like, crude model for how we end up with a series of cyclothems like this in the north of England is one in which we generate some accommodation space and then promptly fill it up. So what we're looking at throughout the cyclothem is essentially a shallowing upwards succession as we fill the hole in. And then for whatever reason, we deepen sea level or we create some more accommodation space in some way, change relative sea level, and then the whole lot fills in again with the same sort of succession of sediments. That's a very crude model, and it's generally been accepted as the way these things work. There's nothing particularly wrong with it, at least at a crude level, although we have to accept that the point in the sedimentology where things get significantly deeper, perhaps, where we generate the new accommodation space, doesn't always coincide with the actual cyclothem's boundaries, because the cyclothem is defined purely by lithology. It's purely limestone to limestone. But it's a crude model, and as a crude basis, it gives an explanation, perhaps, of how we get this cyclicity. So the diagram I've put together over here is very much a simplification of the lower and middle Carboniferous stratigraphy on the Ulston block. And you can see that I've got the main limestones labelled here. There's some sandstones that are not named in between. And all of this other stuff, the sort of mixed sandstone and siltstone of the cyclothem, is represented by the light blue in there. And against it, I've put the cyclothem names here, so you can see how each cyclothem extends from the base of one limestone to the base of the next one. And I should be able to scroll that. There we go. And you can see how the whole succession upwards, all sorts of names. We don't really need to worry too much about those until we get here to the Great Limestone. The colours change a little bit. Just below the Great Limestone is the Denantian-Lemurian boundary. And in terms of lithostratigraphy, we change from the Ulston Formation into the Stainwall Formation. That's the reason the colours change. It's just BGS colours, but don't worry too much about that. It's the same sort of idea. So that's the succession that we're going to be looking at really today. Okay. There's the same succession over here on the left now. And I think it's fair to say that because this Yoredalean type approach has been, I suppose, entrenched in the literature, in geologists' thinking from the north of England for a good many years now, we tend to kind of think of the whole succession when we think about the Carboniferous of the north of England as being essentially pretty much layer cake stratigraphy. So here's this is very cartoony again, but you'll get the point. We're going to come back to it at the end, so it's a useful diagram to use now. But essentially, it's a layer cake stratigraphy of limestone, sandstones, and siltstones. Here's the Ulston Formation, the Denantian strata, basically, and here's the Stainwall Formation, Lemurian strata on the top. Layer cake succession sitting on top of the basement, which is actually a granite batholith that underpins the Ulston block down the bottom there. So that's our model, and yeah, you can kind of understand why that model is so ubiquitous, really. If you look at the landscape, this is the title slide, but you look at the landscape, you can see all of these ridges in the landscape, which are tram-lined, essentially. They're parallel to each other, and those ridges are the hard limestones or the hard sandstones forming the rocks. And I think even when we were mapping up there, and I spent 8 years of my career working for the British Geological Survey, mapping the north of England. This is one of my maps, or part of one of them. And when we were mapping up there, we were kind of entrenched to this idea. And you end up very much with sort of tram-lined geology going through the map. You start joining up disparate outcrops using the model that we have some kind of layer cake stratigraphy here. And that's what you end up with. And if you look at any of the maps of northern England, not just mine, but my colleagues and older maps as well, you'll generally get this impression that it's layer cake and reasonably flat lying. But I think even at the time when we were working there, we were starting to think, is this really true? After all, if you look at this succession, the proportion of limestone, siltstone, sandstone, and so on is actually quite variable in different cyclothems. So how regular is this? That's one thing to notice. We also noticed that some cyclothems actually had sort of partial set mini cycles within them. This is the little limestone cyclothem in here, where the waterfall is actually indicating a partial shallowing upwards and then flooding again, deepening event again. So we've got some of these cyclothems have kind of half or partial cycles within them. They're not clean cyclothems. There we go. And some cyclothems, particularly the time-bottom cyclothem down here, which you'll notice to start with is significantly thick compared to all the others, that has actually complete mini cycles in it, complete with limestone and full drying upwards. So this pattern, this sort of regular, simple layer cake pattern, perhaps isn't quite as true as we think. And also, one of the things that we noticed when we were mapping is that some of these sandstones, particularly in the higher Stainmore formation, but elsewhere as well, they're actually fluvial and quite erosive. So one of the first things I did when the opportunity arose was to put a student on this relatively recently, to look in particular at this sandstone here, which is called the Firestone sandstone. She's just qualified with her MPhil, Viva last week before, something like that. And she did a fantastic interpretation of the Firestone in terms of a fluvial system, drew these lovely diagrams, and came up with fluvial sedimentology that was showing some relationship, perhaps some influence to changes in base level. And she noted that the Firestone cuts down quite dramatically through the stratigraphy in different places. You know, there's arguably at least half a cyclothem, if not more in some places, cut out across the North Pennines by this highly erosive sand body up there. So this is not just a simple layer cake succession on any scale, really. Since then, your pointer is going to drive me nuts. Stick. Does the stick change the slide? Yeah. Since then, we've recognized a couple of other similar situations. Well, my colleague, Colin Waters, former survey now at Leicester, has recognised similar things down here right at the bottom of the succession in the Melbourne Scar in some of the logs and log data that he's been working with, where he suggests anything up to half a cyclothem is missing in places. And we've recognised a similar situation in outcrop around the middle here in the 5-yard cyclothem. So this is not alone. This occurrence at the top here is not alone. We're seeing these sort of down-cutting sandstones that cut bits out in various places. So that's the background, basically. Here's the questions I started to ask. To what extent is that Carboniferous succession actually cyclic? What's controlling the cyclicity, if anything is there? Can we throw a few numerical techniques at it and see what happens, which is literally what I've done, and somehow perhaps contribute to our understanding of Yoredalian type successions? And can we therefore interpret the succession a little bit more robustly, perhaps in terms of substance sediment supply and sea level maybe as well? So that's what we started playing with. And we started playing with it mainly because for the first time, we had access to a complete core through that 500-meter succession. This is the core, or some of it at least, on the left. It was drilled by a mining company looking for possible prospectivity. But they walked away and released it, and we now have access to it. That's my colleague, dressed very health and safety conscious there, from BGS, playing with the core. And as well as looking at the sedimentology, of course, we ran a gamma trace up this core with a handheld gamma type machine that you might be familiar with, this thing down the bottom here. And the reason we did that is that in shallow marine to coastal successions, like this here, gamma is crudely proportional to distance offshore, because as things become more shaly, the value of gamma increases as you get offshore, with the result that we should be able to pick up essentially these shallowing upward cycles in the gamma trace. This is very well recognized from oil industry type work in marine successions. So that was our plan. Okay, so it's a little bit more complex than that because we're dealing with a Yoredalian type succession, which has these detrital limestones within it, and limestones generally give quite a low gamma trace, where we might otherwise expect a higher gamma trace in the offshore. So that's something to consider. And equally, because we normally come to continental deposits in most of these cycles, we often get fluvial stuff at the top that may, oh God, that may be a little bit more high in gamma. So it's not quite such a clear picture, but nevertheless, it's a cycle and it's a succession that you can recognize. It's a pattern that you can recognize. And this is just an example of some of our data. So here's the top of our 480 meter log, as it turned out. Over here, here's the gamma trace in parts per million. Notice I've reversed the scale because I'm a sedimentologist. Geophysicists hate that, but I'm not one. So I'm a sedimentologist, so the low gammas kick over this way, like sandstones would on the log. And you can see some of those cycles. You can just start to pick them out, even this crude level data here. And we're able to do other clever things, of course, with digital data. This is the modulus of the rate of change of gamma, which is a posh way of saying we can pick out all the sudden changes as these spikes here, sudden changes that relate to erosive surfaces where the gamma suddenly peaks or troughs, or indeed sudden changes that might relate to flooding, where we suddenly go from the continental low gamma sandstones to the high gamma siltstones that overlie them. We also, with our tool, gamma tool, can pick up the separate traces of uranium, potassium, and thorium, and then you can start doing some clever tricks, like looking at the thorium-uranium ratio and picking out these really low ratios, which are often associated with flooding events in this type of environment. So in other words, we can do quite a detailed analysis from the sedimentology and the geophysics of this data set. And it is quite a highly detailed analysis, which is kind of hidden behind what looks like a really simple diagram, because this is the end result. So here's the cyclothems, here's the log simplified, here's the gamma trace. And for the first time, I think, I've interpreted a water depth curve from all of that data. So that's water depth getting wetter towards the right here, like that. So that's a kind of result. That's very nice, I think. First result. The first thing to point out is that, lo and behold, and completely unexpectedly, the first 30 meters of this trace actually have a completely different gamma response, if you notice. And that's because they're not actually part of the Carboniferous succession. My colleague noticed this in the field when we were looking at the log. There was a slight angular unconformity and discordance there, completely different gamma trace. That's containing fossils, which we've since had analysed, and this is Silurian in age. And that's actually the first time that a Silurian strata have been recognised below the Carboniferous strata on this part, on this side of the Ulston block. So that's something new that we didn't expect, but we're not going to talk about that. I just pointed out so that you could ignore it. It's a different story that we can come back to later. What I'm interested in, essentially, is the rest of this succession, and notice I've scribbled it out there, is the rest of the succession, which is Carboniferous, is it cyclic in any way? And what can we tell about that? So, ta-da! The first thing we tried was we took our succession and we ran an analysis, which Peter here has had quite a bit of work to do with, looking at ideas of Markov chain for giving us some indication of how cyclic this is. I'm not going to explain Pete's method in great detail. Pete is sitting here. You can talk to Pete or you can talk to me afterwards if you want the detail. But in the interest of time, I'll just show you how this works. Essentially, by looking at how the beds change upwards from one thing to another thing in that succession upwards, you can work out what's called a Markov number for the entire succession. And the Markov number is essentially a measure, mathematical measure, of how cyclic that is. So these are the answers. So here's our Markov number for that succession, just above 0.1. What does that mean? Well, in a very crude sense, the higher the Markov number, the more cyclic it is, or the more ordered, more correctly, it is, assuming everything else about that succession is the same, because that Markov number does depend upon various other factors of the succession other than just its cyclicity. So one way of evaluating that is to take your succession and then randomize it, shuffle it up, and then work out the Markov number of something that is quite clearly just shuffled, random, and disordered. And if you do that a statistically significant number of times, like 5,000, you can end up with essentially a probability density function, this blue line here, of Markov numbers for a disordered representation of that succession. So this is the probability envelope, essentially. And now you can see, you've probably already got there before me, that if this is the envelope of disorder, then apparently our succession, the true succession, also shows very little order because it's right in the middle of it. If this line was out this side, then we could claim that there was some kind of order and cyclicity to this. But apparently it isn't, which is a bit alarming. But then you realize that that's with lithology. And it's not really lithology, is it, that's giving the cyclicity or the apparent order in this. Siltstone can be continental, or it can be deep marine. So maybe working with lithology is not the best way to go. So instead, we tried it with gross facies. There's a little bit of an interpretive element to that, of course, which we have to admit. But we tried it as objectively as we could with gross facies, like that, and now we get a better result. Here's our probability distribution function of disorder, and here's our Markov number for gross facies. And it's to the right of it, which suggests some kind of order and cyclicity in there, but it does overlap with the probability distribution of disorder, so it is theoretically possible that you could generate what we see just by randomness and disorder as well. So that's kind of where we went. And then we thought, okay, well, that's interesting. How does that work? Because, okay, I'm willing to accept that some of this is a bit chaotic, but some of it is also quite clearly showing some kind of order or cyclic nature to it. So we started thinking, and I have to give the credit to this to Chester, who's sitting there, one of my research students who worked most of this out in the computer, but we thought, could we do this evolutively? Could we take a window of data that we sort of move up, that we slide up the log, and work out the Markov number for each window individually and see what that does and stack those together? So we did it, and we end up with something that looks like this. This is Markov number along the bottom, distance up the side. The black line is the Markov number, the sort of instantaneous Markov number for each point as we slide this window up. And the red smudgy bit is the probability distribution function of disorder. So we're representing it by color now, so the darker red is sort of the peak of that disorder bell shape that you were seeing on the previous graphs. And that's quite pleasing. The bottom half here, or the bottom little bit, is actually not very cyclic at all. There's some reasonable cyclicity in there, but a lot of this overlaps with the disorder PDF. And the middle bit, where we do see clear cyclicity in the field or in the core, that's reasonable. We're getting Markov numbers over here, and all of the disorder is over there. So that sounds pretty reasonable. But notice also these big peaks that sort of shoot backwards towards disorder. When I first saw this, I ignored those, as in, yeah, bit of noise. But I'm going to come back to that in a second. They're actually quite valuable to us, it turns out. So that's the first thing we did. We can say, at least objectively and mathematically, that most of the log, or most of the Donantian succession, is reasonably well ordered, apparently, except the very bottom bit, which probably doesn't come as much of a surprise if you understand how sedimentary basins develop and fill up. A little bit of disorder to start with. So, excuse me. That's one way of doing it. Where can we take that any further? Well, if this is a marine succession, we could hypothesize a bit that perhaps these regular changes in sea level that we see that create this accommodation space are somehow related to regular changes in global sea level, i.e. Milankovitch cyclicity, as it's often termed. And if we accept that idea, then we can take our gamma log and we can run analyses on it that decomposes it to look for the various oscillations of potential signal that are in that signal. So this is made up here just to show the point for anybody who's not familiar, but essentially we've got a 40-meter wavelength log there, a 20-meter wavelength oscillation there, 10-meter wavelength, 5-meter wavelength. And if you add them all together, if they're all happening at the same time, this would be the result. And that's what the gamma tool records, essentially that. And we can take that and we can run it through a mathematical analysis which produces a spectral analysis. If you're familiar with this kind of thing, it's just Fourier transform. And you end up with a graph that looks like this. So we've got frequency of signal along the bottom and power, strength essentially up the side. And we end up with strong peaks, these strong peaks, at frequencies that correspond to 40 meters wavelength, 20, 10, and 5. So you can see how that is composed of those signals. Yeah? Here's the result for the North Pennines. The Carboniferous succession. Same sort of graph, frequency along the bottom, power up the side. We're looking at the whole succession in one go here. The red lines, I should explain, that the red lines are a noise model, essentially. A robust AR noise model, red noise model, that defines a way, I suppose, of expressing confidence in these peaks. So if you notice the number, the top line, dashed dot line, is 99% significance, but peaks above that, on it or above it, are not just noise. They are something real in the signal. So the peaks I've picked out, 160 meters, 17, 16, 9, and so on, they seem to be regular peaks of wavelength in that signal. This is lithology scale, so we don't worry about anything down here. And you'll notice that Yoredale scale doesn't really produce anything at all. That's because there isn't really a regular scale of Yoredale. But these wavelengths appear to be in that sequence. That's kind of interesting. But you could also do this the same way that we did the Markov chain. You can run a sliding window up the log, and you can work out what you see in that window. So this is a slightly different diagram, difficult to read, but frequency along the bottom again, yeah, and distance up the log, up the side. And this time the strength of those different frequencies in different places is indicated by the colors. So red is really strong and blue is not there. So you can see how the different frequencies that I picked out in the whole data set, which are indicated by the white lines that I've superimposed at the top, you can see where they're strong and where they're not so strong and how they fit into the succession. Lovely. Trying to interpret that is incredibly difficult. What does that mean? It's difficult because if you think about what's causing these cycles, if we stick with the idea that it is sea level control in some way, then unfortunately higher sedimentation rates image shorter wavelength cycles that you wouldn't see with lower sedimentation rates because you've got more succession being deposited quickly to image it. But also lower sedimentation rates transpose what started off as long wavelength cycles this way. They look like short wavelength cycles because the sedimentation rate is low. So basically we don't really know when you look at these diagrams like this, is it high sedimentation rates imaging shorter wavelength cycles that you can't see with lower sedimentation rates? Or is it lower sedimentation rate taking those long wavelength cycles and shoving them the other way on the graph? It's really difficult to read. But what we can say is that something is changing. I've drawn some sort of key lines on there that divide this graph into a series of separate patches where they have a different character. So something is changing upwards in that kind of way. There is variation in this for some reason. So where do we go from now? Well, we've got that, but it's useful to think about what we actually do know. We have some dates on the Carboniferous succession. These dates are quite new and quite strong. I mean, there's a bit of error, as you can see on there, and that's important. But they are very reliable dates. There's one in the middle there. So we know some dates on the succession. If we know some dates on the succession and we know it's 500 meters thick, we know the average sedimentation rate. That's easy to calculate. So somewhere between 8 and 14 centimeters. The reason there's a variation on that is to account for this uncertainty in the dates. So we're somewhere in that region. Also, because it's Carboniferous and we know the age, we can calculate the actual Milankovitch cycles that we would expect to be present if they are causing any effect in our log. This is the Lascar solutions. So these are the cycles we expect to see: 405,000 years, 125, 95, and so on. And we also know, because we know the thickness and the average sedimentation rate, we can guess at how much sediment that is on average. And we can see that, we should potentially be imaging some of those cycles if they are there. It's in the order of what would make sense with this thickness of stratigraphy. So then we get very clever, very statistical, certainly statistical beyond me, but the computer does it for me. And what we can do is, we can say, okay, if this is what we should see, this is the Milankovitch solutions, the Lascar solutions, and this is our data set. If we fiddle about the sedimentation rate, and we get that to match that, which might then tell us something about the sedimentation rate at the time. And that's exactly what the software does. And it does it statistically. So you run this essentially thousands of times, and this is the best fit answer. So this is sedimentation rate along the bottom here, from 5 to 25 centimeters per 1,000 years. Remember, the average is about 14 through the middle. And this is distance up the side that just matches the log. And the colors represent the best correlation for those sedimentation rates between that and that. So we can see that if we start off here where the red is, about 17 centimeters per 1,000 years is the best correlation that makes that fit onto what we should be seeing. And the white line traces out the best correlation and therefore the variation in sedimentation rate as you go up through that lot. So it's essentially picking out a statistical best fit sedimentation rate and changes throughout the succession, which is really nice. And we have those unconformities. I've called them unconformities or drawn them as such on here. We have where we've got down cutting that we know of, here, here, and at the top there. See how quite nicely that corresponds to significant steps in this graph, which is rather nice. Although there are other steps. But this is completely independent. I'm not fudging anything. It just picks up on those steps immediately. And it picks up on some other steps as well. Here in particular, which is in the little limestone cyclothem. And down here, there's something going on, which is in the Grainbeck cyclothem. So, interesting. Things are coming out. Do they mean anything? What can we do with this? Well, immediately, if you've got a sedimentation rate, you can turn everything into time. From space into time. And this looks like the same log, doesn't it, as before? But if you look carefully, this is now time, linear time upwards. There's the time scale. So linear time upwards, arbitrary, starting at 0 at the bottom, but linear time upwards in thousands of years. And it's not quite the same as the previous log. The space scale is next to it, but you see that the space scale is not linear. So we can turn everything into time, and we can do the same with the gamma trace. This is not the same gamma trace. It's the gamma trace that's been turned into time now. So time is linear in that gamma trace using those sedimentation rates. And we can run that through the spectrum analysis again and see what we get. Just to be annoying, I've turned the confidence level of 99% blue instead of red like it was in the last graph, but you get the same idea. So we're looking for peaks above the blue line, which turn out to be those peaks in thousands of years. There's a 125,000 peak that's quite strong. There's a 70,000 year peak, which is quite strong. 30 and 19, although admittedly 19 is now down in the lithology scale, so that's noise potentially. There's also 1250 up the top there, but I'm not too sure about that. That's something we've got to work on. But these peaks in the middle are quite nice. So we can turn the whole thing into time, and we can do it evolutively in time again. And now we can see what we're really looking at. It kind of tidies everything up a little bit. There's a strong 405 signal, an eccentricity 405 signal in places, and probably all the way through. There's a 125 signal that's prevalent through quite a lot of it. The 70,000 year signal is quite strong in the Visayan, down through here. And there is actually a 30,000 year signal, this one here, which is actually quite good and quite consistent, though it doesn't show it up on that graph because of the color scaling. It's quite weak, but it is there. It's quite nice. So there does seem to be at least some kind of control from these cycles, these Milankovitch cycles, on the development of this succession. Perhaps. Perhaps. But what about where it all goes messy? What about where you get these bifurcations and breakups in the signal? What about these changes? Well, the conventional wisdom in the literature is that these bifurcations occur because there is some kind of break or hiatus in the signal there. And this is the basic idea. Again, it's completely artificial, but we've got a curve over here with a wavelength of 10 meters and no break in it. And then I just broke the same curve at about 60 meters there with a 20% hiatus. In other words, I took out 20% of the curve. And you can see what that does to the signal trace. It deflects it a little bit towards the right. And you start to pick up on a weaker signal on the other side here, a sort of artificial signal. If you step it up to 50% of the cycle, you get a sort of donut. The trace breaks in the frequency plot. This is the frequency plot again. So the trace that we would expect, 0.1 for a 10-meter signal, breaks, and we get a kind of even donut. If you take it up to 80%, the deflection's the other way, and you get a small trace on this side. And you take it up to 100% of a cycle, and perhaps unsurprisingly, you see nothing at all. Because 100% missing cycle is the same as no missing cycle, isn't it? Because it's cyclic. But that's an important result to consider second. So the idea is that these breaks and these circles can in some way represent potential unconformities. And various authors have noted ways in which we could actually measure the amplitude or power values across these breaks. So measure the red there and the sort of blue there. Work out the normalized difference in amplitude. And if you plot that, you end up with this green line graph here. And the key point, this is often referred to as delta mu, but the key point is that the green line will bend towards the higher end, towards the higher frequencies, if you like, when we have less than 50% of gap in the log, or of hiatus, and it will bend the other way when we have more than 50%. And where it bends the most, if you like, the most deflection in both directions, is where the hiatus is supposed to be in your log data. So we can find that, allegedly. We can sort of tune in to that point. But perhaps more importantly than that, these authors discovered that the delta mu value at that point is directly proportional to the percentage of cycle that is missing at the hiatus at that point. That's virtually a straight line. The quadratic is a slightly better fit, but it's virtually a straight line. So if you can calculate that from this signal, you can work out how much signal is actually missing as a proportion of the input signal. That's just a test, which demonstrates the same thing, getting the answers out. This is now hiatus fraction, or fraction of the signal that's missing. Yeah, and 0.2 gives you 0.2, 0.4 gives you 0.39, and so on. It does seem to work. Just try it with made-up data. So immediately, many workers, myself included, start to get all really excited and start drawing things around these donuts that we can see here and say, well, these must be unconformities. And that is not necessarily wrong, but if only life was quite that simple. And it isn't, is it? This is again made up. Here are 4 curves, 125, 95, 70, and 30 wavelength. Add them together, get that result, no hiatus whatsoever. Run it through the Fourier transform to give you a signal, give you a frequency plot, and we get donuts everywhere. We get this kind of effect, which apparently are hiatuses. Hiatus, I don't know. But there's nothing in that. And of course, the reason you get that is because some of these signals modulate each other and interfere with each other. And that's what we're seeing. So are these donuts modulation and interference between frequencies, or are they actually hiatus? Well, of course, we can decompose this. We can bandpass it to decompose it into its original signals and get them all back out, which at least demonstrates that there's no hiatus in there, the artificial data. So I think we need to do this before we start circling hiatus, if you like, or donuts and thinking about it. Here's the same synthetic example, but I've taken out 40% of the 125K, or the 125 wavelength, which is about 50 units. The units is kind of meaningless or arbitrary. You can just about see it because you know what you're looking at. You can see the difference it causes, but remember, in a real-world situation, we don't know what we're looking at. And you decompose that, bandpass it into these four signals, 125, 95, 70, and 30, and you can see it. You can pick it up then as a little donut in them. And you can do the maths. This is the important bit. We took out 50 units, but the maths tells us here that we only took out 38. From this curve, it tells us we took out 33. From that one, it's 62. And from the 30 unit wavelength, 55. So the conclusion is that when you're working really with real data and these signals start to interfere, these calculated numbers are ballpark, for sure. Perhaps the 30 wavelength one is the closest, and that's probably because it's more spaced out and doesn't interfere with the others. The interference ones tend to underestimate. So we need to start treating these numbers as ballpark. That's fine, gives us a bit of an idea. But the other thing to notice is that there's also a little bit of a shift in where this donut occurs compared to the hiatus because of the interference. And that's worth considering. That's important. It's not necessarily bang on the hiatus. Okay? Happy? There's the north of England. So I've decomposed the time signal here to try and pick up on the hiatus. The three that are highlighted are the three that we know about, which come out really nicely. So there's the firestone, sandstone at the top there. Yes, the 95,000 year band gives us a calculation of about 85,000 years for the cycle, the bit that's missing. This one over here, the 30,000 year cycle, tells you it's 14,000 years, but do remember it's only a proportion of a whole cycle. So you multiply that up and you get 74, which is not dissimilar to 85 when you think about the uncertainty in doing this. That's quite nice. The one through the middle is this peak, and this peak, roughly 60,000 years. And Colin Waters' unconformity down the bottom here is about 55-ish years through the middle there. And there's a number of other unconformities that are picked up as well. There's something there around the Great Limestone, again, about 60,000 years. It's nice. There's something in the middle of the Little Limestone, which you remember, Little Limestone cyclothem was picked up in other data as having some discontinuities in it. That's quite small, 15,000 years. If you knew the stratigraphy and you've been in the field, you'd agree with that. There is something there, I think, and it is quite small. There's possibly one in the middle of the Tyne Bottom Limestone, which perhaps explains why we've got these oscillations in there. And that's about, what does that say, about 50 again. And then perhaps most significantly, as yet unreported, we seem to have quite a big one in the Grainbeck section down here. That's interesting. So that's where we got to. There's something kind of working there. It's all a little bit preliminary, but we seem to be getting something. And I can pull that lot together to what is essentially a summary answer. So here's the original log, cyclothems on this side, the dates that we've been using and the three unconformities that we know about, or the three hiatus that we know about. Here's the original sedimentology. Here's the water depth curve that was interpreted from all of the data. Here's the preserved sedimentation rate, calculated statistically. And the graph in the middle shows time along the bottom and thickness, preserved thickness of strata. There's no decompaction in this, up the side. And then an interpretation of accumulated sediment in brown here, the brown line, and a relative sea level curve, the blue line, that together would produce the right water depths to give us that and give us that. So that's an interpretation. And the unconformities are there. So there's the Melbourne-Viscar unconformity. There's the one that we've recognised in the field in the 5-yard limestone. And there is the Firestone that my student recently got her MPhil on. And you can see if you drop down to the time scale, I've put the bandpass filters on the bottom, so you can see how these line up with the donuts or the disturbances in different places. And if you follow across to this way, I've gone back to Chester's Markov chain over here, and just for reference, the evolutive spectral analysis over here. Look how these start to line up with these distinctive peaks in the Markov chain. Those peaks, I don't think, are noise. I think they're telling us something. They are actually picking up on the hiatus breaks. And then you put some of those other breaks in that the cyclostratigraphy picked up on. Well, first of all, before I do that, if we look at the bottom here, this probably isn't cyclic. As we said earlier on, it's a bit messy in here and there's a lot of overlap. So this is perhaps not quite true, what I've drawn there. It's a little bit less predictable, a little bit less cyclic. The bit in the middle is nicely cyclic in everything, with the hiatuses in. And if you look, what I've also stuck in the background here is I've put the original cyclothems but converted into tine on here. And you notice with the exception of the tine bottom and the grain neck, they're all about the same size when you convert to time. And that size is somewhere between 230 and 250,000 years, which is not anything significant, except that almost all of these cyclothems contains at least 2 oscillations in sea level. So those oscillations in sea level, when you divide 230 or 250 between 2, comes out at 125. So is it the 125 eccentricity cycle controlling a lot of this? Tempting to say so, isn't it? Tempting to think like that. And then if I put some of the other little wibbles and unconformities and things that other bits of data have picked up on into that succession, there we go. And we find that they actually line up with other peaks. In the Milankovitch, they line up through here with changes. They line up with donuts in our sample data. And do they line up with actual breaks in the succession? I don't know yet. That's the test. We're going to have to go back to the core store in the north of England, look at this in detail, and look at what we can in the field, which is kind of from here upwards, you can see in that outcrop in the field, and see what we can see and see if the sedimentology adds into that. So it's all a bit preliminary at the moment. It's all a bit, well, let's just see what we can get out of this. And we need to check it out. But it's really producing a very interesting story. This is a conclusion. We're kind of working towards a model in which strongly erosive surfaces are the framework controllers. In other words, instead of the parallel layer cake stuff that we saw at the very beginning, the model probably should look a little bit more like this, and we should be concentrating on these major erosive surfaces, like that, with thoughts, individual thoughts, if you like, about how the sedimentology works in between. We've got some pre-Carboniferous sediments, which we didn't have before. The early sedimentation is unlikely to be cyclic, as I've drawn it here, so patchy. And although authors tend to pick up on a limestone in 2 different logs and join it together, they probably shouldn't. There's no guarantee that that happens. In fact, there's every indication that it probably doesn't. So the bottom bit is not particularly cyclic. The Visayan strata, the bit in the middle here, up to the base of the Great Limestone, Donantian or Visayan, seems to have a 1-2-5 dominant control, which is interesting. That's what's producing the cyclicity that we see, we think. The Murian section is potentially riddled with unconformities. Up in the top here, many of them down-cutting. That's causing us a few problems at the moment in trying to understand that. The causes of many of these unconformities are unclear to me at the moment. And there's an apparently strong 405 cycle in some of it, which I also don't fully understand as to what that means, or indeed what its sedimentary expression is. So what is a cyclothem? Well, it's nothing relevant in terms of sedimentary evolution. strictly speaking. It is exactly what it says on the can. It is a cycle of limestone, siltstone, sandstone, and sometimes coal. On average, at least in the Denantian succession, it is about 250,000 years, but there's at least 2 cycles of shallowing upwards in almost every cyclothem. So I think the main control, the proper control, is the 125,000 year cycle. So that's the conclusions, and I based that talk around the sedimentology and the geology because that's the fun bit. But just to finish with, if we think about some of the implications for this, it's always good to break out to why bother, isn't there? Why do the implications? Well, a lot of this actually lends itself quite well to correlating. A lot of these ideas lend itself quite well to correlating between wells at a subseismic scale, as well as recognizing unconformities. We've actually taken some of these ideas forward to look at recognizing faults in successions as well, because they should work like unconformities. It's not quite that simple. It's a bit more complex than that. We're working on that with Shell, and they won't let me show it to you. But we've been doing those kind of ideas. And, these kind of ways of thinking, I suppose, and this basin scale evolutionary ideas are of increasing importance to the energy transition as reservoirs become larger scale, sealed by lateral facies changes, such as deep saline CCS, where we're looking at basinal scale correlation and understanding, or in situations where the fluid flow questions are basinal in scale, such as lithium brines, nuclear contaminants, and so on. And there is a company currently working the North Pennines as a possible source of lithium. And their main lithium reservoir is the top of the granite where it's in contact with the Carboniferous sediments. At the moment, they have a layer cake Carboniferous succession. Is that right? Will that help? How does that screw up their model? And that is it, I think, yeah. Thank you very much.
So, you're talking about
Time, yeah.
depth.
Sorry?
We've got depth.
Yeah.
So,
what's the timescale from? The timescale is by using the stats and trying to statistically match the peaks that we see in the depth spectrum to the peaks that should be there from Milankovitch in the time spectrum, we can calculate the best fit sedimentation rate and then use the best fit sedimentation rate to convert from space to time, linearly up from the bottom, or progressively up from the bottom. Yes. Yeah.
In Milankovitch style, having soup.
Yes, yeah. The big...
You have a consistency.
Well, yes, you make the assumption that they are there, but if there wasn't anything there that worked, either you'd get ridiculous sedimentation rates to make it fit, or you'd get nothing at all. There is, in that sense, it's statistical. Yeah.
Right.
Yeah.
So that would be gaps.
Yes.
Going on. So you have gappy.
Yes.
So what does that do to time?
Well, again, the time series analysis is done on that window, the sliding window going up. So yes, it smooths over it, but that's where you get a big jump to make it work in the sort of plot. It looks, yeah, if I go back to the, yeah, you're perfectly right, because the gaps are not there in the actual analysis. I could put them back in now, by the way, and that's probably worth trying. Yeah. I could go around in a circle and put them in. Yeah. Because now that we know,
we just suddenly had gaps when you've got
exactly. Which one was it? Have I gone too far? Where's the time one? What have I done? Losing myself completely. Sorry. Just find that. That one. That's the one I want.
You have answered my question anyways.
That's the one I want. Yeah, you see, it does. It's a sliding window, and it assumes, of course, that there's no time gap because it doesn't know anything.
Yeah.
But you get this kind of effect where something funny is happening. Yeah. So what I would like to do, the way we'd like to go with this, if we think we're going in the right direction, is yes, you can put those gaps back in. I could tell it to break there and do it independently, which would then tidy things up again, perhaps, or prove me wrong.
Obviously, it's you're putting your own assumptions in, which is fine,
Yeah.
provided you're honest about it, but it's
Yeah.
showing to see if it works together. Whereas I worry when you're applying
Yeah.
a straight time series analysis without the gaps. Then
Yeah. Yes, we are making that assumption for sure, and we're putting in the gaps, or I'm picking out the gaps. But I think the key thing to notice is you get kicks in this, you get kicks in that, and also completely independently, we're getting the kicks in the Milankovitch, in the Markov from Chester. So we're using different methods to say, well, okay, there's something lining up here. So, you know, can that at least subdue the little bit of the circular reference by assuming they're there or not there in the first place?
I'm quite happy being circular, providing you're straight up that you're being circular and that you're looking for consistency, because you're not going to get anything better.
It's a forward modelling, isn't it?
You don't have any absolute dating in there, which I suspect you don't.
No.
Then you're not going to do anything better than get a consistency. But
it's a forward modelling through to consistency, isn't it? Yeah, yeah, yeah. But we don't know anything. No, we don't. Yeah. Yeah. That is true, but they kind of match up, and I don't want to stand here and say it's definitely controlled by that. It's just a statistical answer. And yeah. It's a simple linear window. Mm. Yeah. Well, they could be. That's true. They could be, but they line up with stuff in other. Yeah. So. Okay, we can try that. Yeah. Yeah. Okay, we can try that and see what happens. Mm. Mm. Yeah. Yeah. You can go round in circles, and I have done many times. Yeah. 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 I know. It is. Yeah. You assume a linear, or you assume the breaks aren't there because that's the way it works. But that's, I mean, part of that argument is why we did it the Markov way as well. See, and it is, you know, the interesting fact is that, you know, it wasn't until I put all this together really, earlier this week, that I noticed how well, there we go, how well some of that lines up. Yeah. Yeah, sure. The finished one, that one. There isn't anything supposed to, well, it's kind of block wide. Yeah. 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 Mm-hmm. Mm. I know. Well, that's what we've been doing from the beginning. No. No, that's just a cartoon to demonstrate that what the point I'm trying to get across is that we should be building more towards a framework, and perhaps the framework is the unconformities, or should be, maybe. Yeah, I'm not suggesting in any way that that correlation looks like that in the middle. Oh, please don't go away with that idea. It was just a cartoon to compare to the first one. Yeah. Yeah. Lithostratigraphically, the Great Limestone is connected through lithostratigraphically to a limestone called the main limestone down our way. And it's like, it was not. Yeah. No, they're not. I don't think they are, but that's what's done. Yeah. Yeah. I'm not suggesting they are the same thing. No, I'm suggesting the complete opposite, if anything. Yeah. Yeah. When you look at the sedimentology in the field, yes, each cyclothem is not just one cycle of shallowing upwards. I think the danger is, although I can be accused of it as well in the way that I started, the danger is working in cycles of sedimentology versus cyclothems. And if anything, we should probably kind of, I'm not suggesting that cyclothems are wrong or not helpful, and they've certainly, they're entrained in the literature and they are very helpful to us, but they are just a lithological pattern. And that doesn't necessarily relate directly to shallowing upwards cycles. And yeah, there's not a direct correlation at all. Yeah. 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 Mm. Yeah. Yeah. Yep. Hello.
Hi. Your order disorder classification, particularly in the low part of the sequence, isn't that just recasting the completeness of the cyclothems? You need one of your early diagrams.
That one.
If you can get.
I can go back to the.
Yeah.
The actual big one. That one. Yeah.
Yeah, that one do. So that little bit is mismatched. But the gamma ray thing's not kicking all the way back to the left hand side. So that would imply that those are incomplete cycles in the thing. So it's actually just measuring the completeness of the cycle.
No, well, if they were regular cycles, however complete they are, the Markov would still pick that up. You wouldn't get the messiness. If we had sort of 3 or 4 fasces, it wouldn't matter how dry they were becoming, if you like, or how complete they were becoming. If it was still an ordered cycle, it should pick it up. Well, the key point is that the numbers that you get out for the Markov number overlap with the answers that you get from just randomizing it. Now, you could argue that if they're not developing full cycles, you haven't got quite as many fasces in that to work with, so it's easier to overlap with the randomness.
True.
Yeah? Yes, or the other way around, yeah. Well, that's the argument that this, when randomized, appears ordered, yeah. That's just the reverse of saying that this is poking, that's poking that way. Yeah. You can't really tell, and I accept that, yeah.
Well, also following Richard's point, then you've got something that's very gappy on a small scale.
Yes. Yeah.
Curve through.
I actually, I mean, I haven't looked at this succession an awful lot down here, actually looked at it. Colin Waters has looked at that, and he seems to, yeah, he proposed that essentially it's very gappy, and maybe that's what you're picking up on in here. But it could be numerous little breaks, and that's a problem. It's a problem for the time as well. The time conversion fits, the point I didn't make and probably should, is that the time conversion fits very well to those dates for the Donantian succession. So there can't be huge unconformities. Well, there could be, because it could all be nonsense. No. I've just got independent dates. They're not, some of them are biostrat, but yeah, sorry, yeah, I mean, where are we? There we are. Those dates are independent, those three there. That's the only control I have. Yeah. Those are independent. They're pretty modern, but you can still see there's a reasonable error in them. Yeah. 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 I have.
To depth curves that you have as well.
Yeah.
So they derive from the sedimentology.
Yeah, and the gamma
question. And then I just wondered, you know, so in that case they're very sawtooth. So your increase in water depth always happens abruptly, and then you get this gradual decline as well. So I often wondered this, but you know, why do we see that in the sedimentary record then? Why do we often see kind of you know,
sudden deepening apparently?
Those you see all the time with a very
one simple answer is that if you flood, bring up the water depth and flood and transgress, you effectively at the same time at that point reduce the sediment supply quite dramatically, because most of the sediment's dumped to the coastline. So you shut down the sediment supply. So actually there is a deepening, there should be a deepening in the sedimentology, but it's preserved in that much as opposed to the shallowing, which is that much, which on that scale looks sudden.
That's great, thanks.